Looks like I'm live. Welcome everyone to the second of our two classes today. I'll deliver some sort of important announcements, I guess, here in the beginning regarding the quiz and the test. I've been scrambling a little bit to figure out how to do all this via Blackboard to make it as easy on everyone here as I could, and also to make it a little easier on me. So three major changes, I guess. Number one, the activities now are in a different spot. They're marked as assignments. I've been told that using the assignments that if you photo them, you can send them back to me either as I think it's a PNG or a PDF. Send back to me as a file, and that way I can see the assignments a little more clearly than I could with just the photographs that I was getting. I think I've had 5 eye surgeries over the last 10 years, so it was really getting some pretty serious, severe eye strain. I'm trying to make that out, and plus if they're shared on Blackboard, I can have some of my graders take a look at some of that work as well. It was one thing grading, one copy per group or one copy per table. It seems like I'm grading a lot more now than what I used to, and it's just so hard. So see if you can resubmit those on that assignments page. If not, I'll make that work next time. Today is the first quiz since we've separated ourselves physically. It's a quiz where it's a multiple choice quiz. I already tell you what the answer is. I just want to make sure that the logistics and the system is working the way that I want it to work. That way I have a little feedback going into Thursday's exam. I've chosen not to use Proctorio for a little while, just to make this go as seamlessly as I possibly can, both for you and for me. So there's no Proctorio that'll be needed on today's quiz, and I'm not going to have the next exam monitored either, so you're on the honor system on that one. So I believe it's at 4 o'clock tonight that the quiz should open for you. It's in the quizzes and tests folder on Blackboard. Click it, open it, click the right answer, push submit, and that should take care of that. That should be done, take you a minute maybe, since I give you the answer, but I just want to make sure all that works. Friday's exam will start right at the start of class, and I'll give you an hour and 15 minutes on it. I've been working on the exam quite a bit in the last several days in particular. The old exams that I based the course on, I've been refining those, and I was a little sad not being able to use them. I asked my wife this morning. I was really distraught having to, throw away all that stuff that I worked on for a number of years to get just the way I wanted it. But as I created more questions on Blackboard, I decided that it was going to be okay. I could still make some really good questions, and just the format slightly different. It makes me think a little bit more how I'm going to ask a question so that I can get so that I can see that you know what's going on. The exam on Friday, it looks like it's going to be 20 questions, probably 15 multiple choice, and then 5 of them will be short answers. Show Cat. Cat's not here. I'll see if my wife can find the kitty. Hey Renee, can you find Squeaky? Okay, she wants to make an appearance. They want her to make an appearance on the video. Okay. All right, Brian. My wife is going to go get the cat, and she might make a brief appearance here today. She's probably going to be just awake, and we'll see if that's going okay. So anyway, that's the initial stuff. I did want to mention a couple things on activity 16, if I could. The first 2 problems on 16, if you look at the second sentence, I wanted to know something about the second derivative test. So on problem 1A, is she here? Yep. Thank you. Come here. There's Squeaky. Say hi to the folks, Squeaky.
Yeah.
Thanks, honey.
You're welcome.
Yep. Squeaky also made an appearance. She always follows me upstairs because that's one of her favorite places to be. My office here, my temporary office is upstairs. So she thinks I'm going to go upstairs and pat her. So she's always right here at the start of the 2:15 video. And then she leaves pretty disappointed after a few minutes. So back on activity 16, here's part A. F prime of 20 is equal to 0. F double prime of 20 was bigger than 0. There's 20. So we need to draw a graph that has these two things going on. The slope is 0 and the graph is concave up at 20. It doesn't really matter what it looks like over here, but at 20, it must look something like that. So it must have a slope of 0 and be concave up. Now here's what a number of you were missing. Notice this, the second sentence says the results yield the second derivative test. Okay, so at x equal 20, the function has a or has an. Well, the second derivative test tells us whether at a critical point we have a relative maximum or a relative minimum. This one has a relative minimum. If you go on to part B, that'll have a relative maximum. There's also some issues regarding the charts on problem 3. And let me make the charts, I guess, one more time as well. So this is on activity 16. Those were probably the two areas that I thought were done the weakest. So here's problem or activity 16, problem number 3, the two well-made charts. Here's G. Here's G prime. Here's G double prime. G gives me points on the graph. G prime tells me whether the function is increasing or decreasing on an interval. G double prime tells me whether or not the function is, or tells me whether the function is concave up or concave down on an interval. So what I'm going to do first when I make my chart is I'm going to consider this derivative. This tells me whether the function is increasing or decreasing. If I set it equal to 0, that's when the slope is 0. That's when it's neither increasing or decreasing. And that's going to give me the borders between increasing and decreasing segments. If I set that equal to 0, I notice that this is a quadratic. However, this is a factorable quadratic. So let's factor it. Factor out a 3x, left with an x minus 4. Set that equal to 0, and we get two spots. X is 0 and x is 4. Now, if you wanted to, you could plot these ordered pairs. Eventually, we'd have to plug in x equals 0, plug in x equals 4 back in the original. This one is -5. This one is 64 minus 96 minus 5. This is minus 39. Again, that gives us the points on the graph. This tells us whether it's increasing or decreasing. So now I'm going to use this derivative. It doesn't matter which form I use. I'm going to use that derivative to help me make a chart. And the charts were not well labeled and not clear at all. And I want these to be really clear. So the intervals go there. The test point goes there. The value of the first derivative, g prime, goes there. And then the behavior of the graph goes at the bottom. For this, all this first chart deals exclusively with the first derivative. First derivative tells increasing or decreasing. So we know it's neither increasing or decreasing at x equals 0 and x equal to 4. My first interval, therefore, will be all the numbers before the first critical point. The second interval will be the numbers between, the interval between the two critical points. And then the last one will be from the last critical point to the end of the graph. I'm going to choose a test point. Any number that's in here will work. Here I'll choose -1. Here I'll choose 1. Here I'll choose 0. You can choose whatever you want, it doesn't matter. Now I'm going to plug whatever test point I have back into my first derivative, and it doesn't matter where. It's a little easier for me in the factored form. So if I plug a -1 in there, it's -3 times -5, that's 15. The function is increasing. If I plug in a 1, I get 3 times a -3, that's a -9, that's a negative number. The function is decreasing. If I plug in 5, it's 15 times 1, that's 15. The function is increasing. Okay, so I know the function increases, decreases, increases. I remember that from before. We'll keep that in mind. That all dealt with the first derivative. That tells us nothing about the shape. The second derivative tells us about the shape. Again, we'll set this equal to 0 and find the place where it has no shape. In other words, where it's perfectly straight. If I set that equal to 0 and solve, I find that x is 2. So I'm going to plot that point on exercise 4 as well. If I plug 2 in there, I get what? 8 minus 24. That's -16 minus 5 is -21. So there's the third point on the graph. Critical point, and that point right there is called the inflection point. That's where it changes concavity. Now the second of the two charts. The labels on the side are pretty much identical. This will be interval, test point. Here's the only difference. Value of the second derivative in behavior. We had critical points at 0 and 4. That has nothing to do with the shape of the graph. The shape of the graph is on the second derivative. There's only one place where this graph lacks concavity, and that's when x is equal to 2. So my intervals will be from the numbers before 2 and then the numbers after 2. Not 0, not 4. That has nothing to do with the shape. That has to do with increasing and decreasing. Choose a number. I'll choose 0 and 3. I'll plug those in the second derivative. This one is a -12. Plug 3 in here. 18 minus 12 is 6. Since the second derivative is negative, this is concave down. And since this one is positive, this one will be concave up. Okay. So there's this, and again, this really, both those tables lacked a lot of detail. Go back if you wish and look at my original video of when I introduced this way back, gosh, right after the last exam, I guess. Now, if I'm going to go graph it, everything is pretty well laid out for me. I have just a few points, 0, -5, 2, -21, 4, -39. Those are the only 3 points that I need. The function, remember, increased, decreased, and increased. It was concave down till we got there and concave up afterward. So here's the graph. Concave down, concave up, done. I have that graph almost perfectly drawn. It doesn't do anything after that because I've located all of the critical points and I've located the only inflection point as well. So look at your work on activity 16. Make sure that you understand how that goes. All right. Any questions on as far as what's coming up today? Any questions on activity 17, activity 16, activity 15, the exam coming up, the quiz coming up? You have my undivided attention until the last question is answered. I believe I have the quiz scheduled to open in this class. I set a timer on it. I believe it's scheduled to open exactly at 4, and then it'll close again at 5. I'm going to double check that just to make sure I have the timer done the way that I wanted it done. So bring on your questions if you have any questions. Quiz for today. It should open up at 4:30 if everything's going according to plan. Question 1, 17(1)E, question 3, question 2, and question 1. All righty, I guess that's everything, isn't it? We'll start from the beginning and work through these sort of step by step, and I'll let you fill in the details as we go through. All right, problem number 1, activity 17. What I like to do is sort of prompt you as my students to think about, well, what would you do if you knew what something was, and allow that to structure your thinking where you don't know what something is. And this first problem is a nice example of that. So here's the building I have to build. I don't know how to build it yet. I know it's going to be a rectangle. I know it has a front and back and 2 sides. I know it's a lot more expensive on the front side because that's where all the pretty decorations go. Less expensive. If you walk through any downtown, you see how pretty the fronts are, and the backs and the sides are always nondescript concrete block. So you want a nice little entrance to make things look good. We need some floor space. 120,000 square feet. The formula for area of a rectangle is length times width. So we know that this times that has to be that, regardless of how we orient or how we make this one. Okay, so let's say we're going to do the known side and we're going to do the unknown side. So let's say the front and back are 300. So let's say that this front, in the first case, front and back are 300. So I'm going to work through, here's part A. I'm going to work through that simultaneously with part C. Part A, this is 300 feet. On part C, the front and back are X. So if I draw this rectangle one more time, and this is 300, can I come up with what that other dimension must be? How would I do it? So the front and back are 300. What are the sides? And I'll do the same thing over here. If the front and the back are X, and that's 300, that's 300, if the front and the back are X, what would be an expression for those 2 sides? So first I'm going to work it with a number I know, and then I'm going to allow my imagination and my scale to work it through with an unknown X. All right. Here's the constraint. Here's what we've decided. What do those other 2 sides have to be if this side is 300? Yep. And I'm guessing, Stacia, you got that because you knew that that times that has to be this, or this 400 was 120,000 divided by 300, right? So if this is X and this is X, what would be an expression for the length of the 2 sides? I'm going to do the same situation. You're going to do the same setup as you did on this one. How did you get that 400? Well, you took this divided by that. So what's an expression then for the length of the 2 sides if the front and the back measure X in scenario number 2? 120,000 divided by X. Okay, so far so good. Now we're going to calculate the cost. This scenario right here, the front and the back are 300 and the sides are 400. What's the front going to cost? Remember, the front was the more expensive. Every linear foot of that was $450. So the front would cost $450 per foot times 400 feet. How about on this one? What would be an expression for the cost of the front? I'm going to put this triangle up there. Yeah, this rectangle up here one more time. This one was X. And that's 120,000 over X. The numbers, this one we know. This is 300. That's 400. Wait a minute. I screwed that one up, didn't I? Okay, wait a minute. The front was 300 yards long. Is that right? 300 feet long. It was $450 per foot. There we go. So what would be an expression then for how much is the front going to cost if we design it with a front and back of X feet in length and the sides of 120,000 over X? What would be the cost of the front? Cost of the front, cost of the back, side one, side two. See if you can fill all those in. Yep, 450X it is. Let's go right down the chart, tell me what each of those are. What's the cost of the back going to be? And I'll do this one. It's $200 a foot times 300 feet. What's the cost of this one side going to be? It's $200 a foot times 400 feet. What's the cost of the other side going to be? Well, it's going to be identical, isn't it? If someone would total those up for me, I'd appreciate it. So now let's work on those. Let's see if we can come up with expressions for how much the back is going to cost, how much each of those sides are going to cost. So as you figure out either what this total comes out to be, or you want to put those in there in the little chat box, I'll be ready to copy them down. Yep, 200X it is. All right, $355,000. All right, so we got the front, the back. Now we have the side one and side two. Each of those were $200 a linear foot. So what would be the expression that goes in each of those? Yeah, I like that. That came out right according to my quick little mental calculation. Good job, Tommy. Yeah. It's $200 a foot multiplied by the length of that one, and of course the side too is going to be the same. So how do I calculate the total cost? Well, I add all those pieces up. So I'm going to add this, and this, and this, and this. Let me simplify those a little bit. Since we have fractions there, we can multiply together. I'm multiplying the numerators, 0, 0, 0, 0, 4 zeros, 2 more zeros from that. 2 times 12 is 24. So both of those are 24 million over X. If my mental math was correct. Let me check the number of zeros again. 4 zeros, 6 zeros. Yep, I like it. Okay. So if I add up all of these costs, I'm going to have the variable cost function. See, adding those two is a piece of cake. 650x plus, adding those two up, since they have the same denominator, that makes the job a lot easier. 48 million over x. There's the function that we want to minimize. We want to get that cost as small as possible. But we are limited with a domain as well. X must be bigger than or equal to 300. Just because of aesthetics, we don't want this skinny little building on a lot that looks dumb. We want it to fill up the frontage of the lot as best we can. So if you look at this function right here, we did functions very similar to it on at least 2 of the previous 3 activities. Plus we did a function, this equation works a lot like the cost function on the, what are those called? Inventory type problems. A linear case, and then a rational function with an x in the denominator. So the algebra and the calculus on this one works pretty well straight through the rest of the way, as you might expect it to. I'm going to sort of leave this one go for right now. I'm going to let you work the algebra and the calculus. As I recall, I think we got a minimum point at x was equal to, if I'm not mistaken, it was like 271 or something like that, is where that function had its minimum value. And of course, that's not in the domain, right? So the smaller the x, the less expensive it's going to be. So if you look at, this is the only critical point, by the way. I'm going to consider what the graph is. At 271, this cost function minimizes. And then after that, it goes up again. There's no other critical point there. So once this function starts taking off, you can pretty well bet that at 300, you're going to have the minimum allowable cost. Again, the minimum cost would be when x is, now again, don't quote me on this exactly, but I sort of recall from my 215 class that someone got up about a 271. We didn't work out the problem all the way through in that class either. But I do recall from looking at other students' work that the x value that minimizes this cost function is less than 300. However, the constraint of the equation, the allowable domain, makes us say that, okay, we have to build this building 300 on the frontage. In fact, that's what we did in the very first problem, wasn't it? So we already know what the minimum cost that the company is going to have. It was at, what, $355,000? Yep. So that wraps up problem number 1. If you have any more questions on that, let me know. I'm going to turn my attention to problem 2. If you're struggling, by the way, if you're struggling with how to come up with this, send me a note. We can work on it a little later. Jot that down so I don't forget what the function was. All right, on to problem 2. problem two, I again had sort of the training wheels on. I said, okay, if this is this, then what happens? So we're going to work parts A, B, C, and D, and then E, F, G, and H sort of simultaneously. Some of the students in the first class had a little difficulty understanding exactly what that original function is. So the price-demand equation, that's a typical demand curve in economics. So say this is the price, this is the number demanded. As the price goes down, the quantity demanded goes up. Vice versa, as the price go up, you get fewer and fewer articles being demanded. So that's sort of the shape of that P of X function that I've given you there in the very beginning. So P of X is that where X is. So let's see, can we find the price for a demand of 6,000 computers? So what would that be? How would you do it? When will the quiz going to be posted? It's posted, it should open up exactly at 4 o'clock. So on to part A, on number 2, find the price if the demand is 6,000 computers. How are we going to do that? And what would that number be? Yeah, and how did you get that number, Stefania? Yeah. Yeah, so we're gonna find out that the price if we just plug the number right in. So we're gonna calculate P of 6,000, and that came out to be about 1,360. I'm just going to round it to the nearest dollar, if you don't mind. Okay, so there's part A. We're going to, if this was the price for 6,000, in part E, they're asking us, well, what's the price if we manufacture X of these computers? Well, P of X, according to the formula, is and this is a nice way to start on a problem like this. If you don't know any place else to start it, you pick a number out. I picked 6,000. Why not? Why? Because it's one of them in the demand or in the domain. Okay. Now, eventually, I want to maximize the profit, and I realize that profit is what you get when you subtract off the cost from the revenue. So I'm going to have to come up with the revenue next. Part B, find the revenue generated by a demand of 6,000 computers. So this is the demand, 6,000 computers. This is the price, right? It's that many dollars per computer. So what would be the total revenue if we build 6,000 computers and we sell them for $1,360? We'll multiply those two together, whatever it happens to be. I'll let someone with a calculator do that. That's the number of computers sold. That's the price per computer. How many dollars is that? And then we're going to march over. So if someone's working on that, while we're working on that, let's consider, well, how are we going to do this one? Here we knew X was 6,000. Here we're just letting X be X. What would be the revenue if we're manufacturing this many computers and selling them at that price per computer? 8,161,500, exactly right. The benefit of me looking at this problem both yesterday in the review session and then in my 215 class as well. Okay. Great job. So now we need an expression over here for the total revenue. I'm going to call this, I guess, R of X. So this was the revenue when we did 6,000 computers. We multiplied this number times that. We'll do the same thing over here. This is the number of computers we're manufacturing. That's the price per computer. So everyone's in agreement on that one. Let's come up with the expression over here then for the revenue if we could. Sure, yeah, it's the revenue is the number produced times the price per. So it's going to be X multiplied by 1,500 minus 0.205X to that same power. And if you wanted to, and I'm probably going to have you do that in this case because it's easier to take derivatives, let's distribute that X through there. 1,500X minus 0.205X to the 1.75. Right now we have to consider cost, and this is sort of the classic cost of production model. It has a fixed cost of $800,000 per year. So if we're manufacturing anything or we're not manufacturing anything, we have that overhead of $800,000 that we're paying. Things that would fall in that, maybe you have a labor contract, you have to shell out this much money. Maybe you have rent, maybe you have a building loan. But those are things that are unretractable. You must pay that much money whether or not you are manufacturing, in this case, computers. So when I come up with the cost function, I know that I have $800,000 no matter what. That's built into the process. Now, each computer that I make is going to cost me a little bit more. That's sort of the marginal cost idea. In this case, the marginal cost was $85 per computer. So if I make one computer, it's this plus 85. If I make two computers, it's this plus 85 times 2. Things that would fall in the variable cost would be raw materials. Probably labor costs have a variable cost to them as well. The more you make, the more labor it's going to take. Energy costs certainly would be in the variable cost. But this is the easiest of all of the possible cost ideas, the fixed cost and variable. Let's see, it's $85 a computer. And if we manufacture 6,000 computers, whoops, forgot my zero. If we manufacture 6,000 computers, someone tell me what that number adds up to. And then we're going to come up with exactly that cost function where X is the number of computers we are manufacturing. So someone tell me what this number is. Someone else tell me what this cost function should be. Oh, so that's 130, okay, 1,310,000, good. So if we make 6,000 computers a year, that's going to be our total cost, a little over, I guess, 1.3 million. If we manufacture X computers per year, what would go right in there? Sure. 800,000 plus 85x. Now what we were assigned to do in this problem is find the profit. Okay, so now we're going to find the profit. Profit, let's see, that's the amount of money we have coming in. That's the amount of money we have going out. The difference between those two will be the profit. So if I could do that subtraction, I think I can do that mentally. I'm going to have you, GH, I'm going to have you come up with what the profit function, this is capital P now. So I'm going to define that differently from the original one, make this look like a smaller p maybe. So that was my price demand function. This is the profit function, P of X. Someone do that subtraction with a little algebra to it, simplify it as much as possible. I'll do this subtraction because I can. It's lined up pretty well, 0, 0. Whoops. That's a 5. Let's see, that's a 1. 5, 8, 6. Gosh, I hope you did that right. $6,851,500. Does that look right? So now let's see if we can come up with what the profit function is. How to calculate the profit? In this case, I took the revenue minus the cost. Doesn't matter if I'm building 6,000 a year. If I'm building X a year, the profit is always the revenue minus the cost. Okay. So what function in here, the function that I'm eventually going to maximize, what is the profit function? I like it. Yep. Yep. So this minus this, remember to distribute the minus function. I think I'll copy it down just as you got. Yep. So the like terms are those two. 1415x minus 0.205x to the 1.75 and then minus 800,000. That's the profit function. And if you want to check your work, if you plug in 6,000 for X, you better get back that $6,851,500. That's the function that we want to finish up. Now I'm going to summarize this one. So here's part E, I guess the second part of part D. Summarize. Okay, so if the price is set at $1,360 a computer, we will sell 6,000 computers. Our revenue will be this. Our cost will be this. Our profit will be this. Okay. If we set our price at this many dollars, we will sell this many computers. If we sell this many computers, this will be our revenue. This will be our cost. That will be our profit. So we know what each of those things is. Now we want to maximize the profit. So let's get started on that one. I think I'll work this one all the way through because this is a little different than a little different type than what we've had for just a little while. And I did get, I'd say 4 or 5 emails with people who got so far on this one and then sort of had the wheels spinning. So let's work this in together, shall we? So this is a function I want to maximize. Let's go with the first derivative. I'll do that for you because it's a simple one. 1415x, the derivative of that is 1415 minus. Oh, here I'm going to need someone with a calculator, I suppose. So we have that coefficient multiplied by that power, and I don't think I can do that mentally. So someone help me with that one. Minus a fifth of that. It's got to be 0 point something. I'll fill that out. X to the reduce the power by 1, 0.75. And then the 800,000 subtracted off is a constant, and the derivative of constants either added or subtracted off. I'm bringing it back to 0. Okay, so someone, if you'd be so kind, tell me what that number is that belongs in there. So taking the derivative of that second term, negative 2.05x to the 1.75, using the power rule, what should that coefficient be, please? Negative 0.0624 could be. I think the decimal's off a little bit because that's, whoops, copied that wrong, didn't I? 0.2. So negative 0.2 times 2, that's got to be bigger than 0.2. So maybe your decimal's off on this one. So negative 0.205 multiplied by 1.75. I'm guessing it's somewhere around a 0.3 maybe. Maybe 0.4, maybe 0.5. Yeah. 0.3, yeah, I like that. 0.35875. I wish myself plenty of room. That seems to be, yeah, that seems to be right on. So there's the equation of the first derivative. If we want to maximize this, of course, we're back to the regular steps. Sometimes this is increasing, sometimes it's decreasing. We want to figure out exactly what it's doing. We want to find out when this hits its maximum point. We want to take the first derivative and set it equal to 0. We're looking for the place on the graph where the slope is 0. All right, so setting that equal to 0, we have a benefit on this one, and one of the things that I look for every time I solve an equation is I want to see how many times the variable appears. And it's only there, and it's only there once. So if it's only there once, I can manipulate it around. I can solve for that by moving everything else around. I despise working with negatives. I find I make mistakes when I do. So I'm going to add that to both sides first. 1415 is 0.35875 x to the 0.75. Solving that equation, what do I do next? Yeah, the quiz won't show because the quiz is not showing up on Blackboard. All right. Let me see when I started. Maybe for you, this group, I started it at 5. $4.30. Okay. All right, take a look at the quiz now. Yeah, it should have opened at 4:30. Yeah, and I just there's a thing that a checkbox that said make available for students. So now, if you go into Blackboard, see if it's available to you. Yay! Thanks, Emily. It's a toughie, let me tell you. You know, I had to practice for hours figuring out what that one was. Okay, so back to this. Let's see if we can solve. What's the next step? Yep, divide by that. And if you divide both sides by that, you get x to the 0.75 is equal to, oh man, I think this was like 60,000 or something. We worked it out earlier. That's the best of my recollection. Multiply that by 3. No, that's too soon. Okay, yeah, someone with a calculator here, tell me what that division works out to be. About 3, that should be about 4,200, 4,300, I bet. $39.44, okay. Yep, and now somehow we have to get from this to the end. And that was the one step that so many people got hung up on. Here we have x to a power. If you wanted to, you could see if this was x to the 3/4. Not that that's really going to help a ton, but it doesn't hurt. So what do we do to both sides so that this exponent is no longer a decimal or no longer a fraction? So I have to do the same thing to both sides of the equation. Here's a little hint. If you had, say, x cubed was equal to 8, you took the cube root of both sides, and the cube root is the same thing as the 1/3 power. So you took these to the reciprocal powers. Yep, take the reciprocal powers. So I don't care how you do this. You can either do this as the 4/3 power if you wish, or if you didn't convert that to fraction, you could take this to the 1/0.75 power. That would work just as well. And when you do that, I think here's where we got 60,000 and change. Yeah, you could do it as a root too if you wanted to, sure. This ends up being the cube root of 3944 taken to the 4th power. That also works. So there's all sorts of different ways that you can get from this power function to the answer. This comes out to be 60-some thousand, as I recall. That tells us x. That tells us how many Computers we should manufacture. And I think, I'm just going to sort of write some of this down. I believe this was 66,000 maybe. All right. If someone has, yeah, okay, 62,313. 318. So there's the number of computers that we should manufacture. If we go back to step A, small p of 62,318, that'll tell us the price that we should charge per computer. Again, that's that very first P that we looked at. If you want to calculate the revenue, 62,318 computers, how many dollars of revenue we would have. You could calculate the cost of 62,318, and then finally you could calculate the profit of $62,318. And those would be nice numbers to have in the summary statement at the very end. So we know, first off, how many we're manufacturing, 62,318 a year. We know what the price would be per computer. That's going to be really important information. We have to know how to price these things, the revenue, the cost, and then the final profit. And the profit you get here should be considerably more than we had the first time we worked this problem when we were manufacturing 6,000 computers. I'm not exactly sure what that profit was, but I know it was substantially more than we got in Part D. The constraint is 60,000. Hey, you're right. Ooh, nice catch, Jessica. The constraint is 60,000, so we can't make 62,318. It looks like we're stuck making 60,000. Good catch. So we're going to our maximum capacity. Calculate all of those. Now we can figure out what the price is for manufacturing that many, the revenue, the cost, and the profit. Huh. Funny, I didn't notice that one. Worked it through earlier. No one else noticed it either. All right. On page 3, problem 3. Now we've done this problem in a slightly different variation. I think it was on the last activity. If not 16, it was on 15. Yeah, thinking back was on 15. In that case, we were thinking how many fruit trees we were going to put on each acre of land. Same basic idea here. The only difference between this one and that one is we're growing a different crop. And on that one, I said, okay, if we plant them this thick, what's going to happen? I didn't give you that prompt on this one. So I'm going to have you sort of lay out a scenario on this one where you have a known number, and then you have an unknown number. Okay. So reading through it, we have a density of plants. There we go. X is the number of plants per acre of land. So here's our demonstration of an acre of land. Again, it's 43,560 square feet. There's a little wheat plant seam in there. I'll pretend they're wheat. I don't know what it is. There's little wheat plants growing in there. I got a ton of them in there. Each of those little plants has so many seeds on it, and it produces so many pounds of grain. If I compact them in there too tightly, however, each plant will suffer and won't produce much grain. There's too much competition for limited resources. If I have them spread too far apart, they have plenty of resources. So each one will grow a lot, but they're not in there very tight, so they're not going to get much. So we have to strike the balance between too tight and not tight enough. Okay. Create a function that'll find the number of pounds of grains on 1 acre of land could produce if we planted it X plants per acre. Okay. So let's say, so what do we have between 100 and 8,000? Let's say we decide to plant in 1,000 plants per acre. Over here, we'll do X plants per acre. let's see if we can figure out, if we do this, what's the total yield on that acre of ground going to be? And if we can do it with numbers, we should be able to do it with unknowns as well. So if I know I'm plugging in 1,000 plants per acre, what else do I know about this scenario based on the first line of the problem? Yeah, we have the formula. We have a formula that tells us what. So if we plant 1,000 plants per acre, what's that gonna tell me what that's gonna yield for us? Okay, yeah, we do get a number. If we plug in AY of 1,000, we get 0.2678, I guess, if we round. That means for each of our little blades of cereal grain there, each of those on average is going to have that many pounds per plant. Okay. AY of x, the general case is just whatever that function is, 1.2 e to that power. 0.0015. So now we have to analyze what this is. Okay, we're putting in 1,000 plants on every acre, and each plant is going to produce that many pounds of cereal grain. So how many pounds of grain will we produce on each acre? So what do we do with those? What do we do to calculate this many plants per acre? this many pounds per plant, what can we do to come up with the number of pounds of grain that we're going to be able to produce on each acre? What do we do? Yep, multiply by 1,000. So if we multiply this by 1,000, we get 267.8 pounds per acre. We'll do, of course, the same thing over here. Well, number of plants per acre times the yield per plant, 1.2 e to the negative 0.0015x. That whole thing multiplied by x. I guess I'll put the x right up the bottom. That's the function then that we want to maximize. We want to get as much yield on each acre of ground as we possibly can. So there's the function that I'm calling y of x. I'm going to erase everything I have here and concentrate on this. Again, I'm going to work this one almost all the way through the end, and I'm going to leave the last couple of steps to you because we're starting to run a little bit out of time. Y of x is equal to 1.2 e to the negative 0.015x multiplied by x. Let's take the derivative. We want to take the derivative, set it equal to 0. When we take the derivative, we're going to have to look for the correct rule. So look at that really carefully and tell me what rule you're going to need to use. Product rule it is. Two functions of x multiplied together. So let's see if we can carry out product rule. So let's see, we can call that f, that g. What will the product rule yield? It doesn't matter which way you do it. Anyone ready to venture a guess? What does the product rule yield? What will the first derivative of that yield function look like? All right, it's getting toward the end of class. I'm going to let you ponder this one. If you have a breakthrough and get it, and you want me to check your work, hey, send me a note along. I'll check it. Otherwise, we could take a look at this at tomorrow's review as well, if you're still interested in that. We do have 2 reviews coming up for the exam. The first one is going to be tomorrow at noon, and the second one will be Thursday at 11. So look forward to helping you get ready for those exams. Hopefully the quiz went okay today. I'm anxious to get into my grade book and see if the grades showed up the way that I wanted them to. Hopefully at least one of you was able to get to it. The quiz is open until 6, so if you haven't had a chance to do it yet, log in back to Blackboard, open the quizzes and test folder, click on quiz 331 and have at it. Okay. So I'm signing off for now. We'll look forward to, I have another class coming up fairly soon. I need to get a little bite to eat. I'm looking forward to hearing from you sometime tomorrow.